Assalamu alaikum. So previously we discussed about corners and scale invariant feature transforms, feature descriptors, histogram of oriented gradients, range sec, and image segmentation in our online video lectures. Now let us discuss some of the aspects of machine learning in this week's lecture videos. So I'll go through some of the machine learning algorithms, but not in the deep sense, but just I will explain them in an abstract manner, so you have an idea that what machine learning algorithms could be used in a certain situations with certain data modalities. So let's dive into it. So we have already learned about image formations. We have already learned about gradient, edges, corners, descriptors, and how to extract features from them. Now from this stage we can either go towards the recognition process or the reconstruction process. So the path which we will take for the couple of weeks now will be towards the recognition process rather than the reconstruction process. So we will focus on the recognition aspect. So often we need machine learning for compact descriptions of the visual world to perform some kind of scene recognition, like what kind of scene an image is representing, or to find something like to locate objects or to find some objects in a particular image. So I'll give you the examples of both. So basically the recognition process involves all not the recognition process is not just limited to these two applications such as scene recognition or find pedestrians, but these are these are two of the applications which actually explain it in a much better sense, that how we can perform the recognition process. So these are some of the scene recognition examples which I have re-engineered so far. So you can see that by visualizing this image, the place tags which are returned is dam, which has the probability of 18.46%, and cliffs and canyon valley. So these have some of the probabilities assigned. So, and we can find all of these kind of objects or kind of scenes in this image. So we can say that okay, all of these elements are actually present here. Similarly, for this image, it is a mountain path, Zen garden, valley, forest path, something like that. So all of the probabilities refer to some of the scenes which can be considered as a part of this image. Similarly, there are other examples. In this, lighthouse yields the maximum probability, palace yields the maximum probability in this case, and greenhouse indoor yields the maximum probability, which is 61.08%. Similarly, downtown skyscrapers yield the maximum probability. Formal garden, pond, topiary garden yields the maximum probability in this case. And then the lecture rooms, classroom, and mountain snowy. This is the image of Lake Saiful Maluk in our country. So I think it's quite obvious that it tags the places like mountain, snowy, and glacier. So this is a kind of the example of supervised learning, where you have a pair of images and its labels, and based on those labels we actually train the network, or we actually go through the machine learning pipeline to recognize a particular place or assign a particular place tag to an individual image. Now, the approach which we will take in this lecture videos is that we will look at the machine learning as a tool. I will not go into the details of each learning method, like I will not explain that what is the mathematics behind all those machine learning algorithms, but I'll just explain it in an abstract way so that you may know how those algorithms work. And of course, I'll not pick all the algorithms in that particular category. I'll pick some of them and explain it that how they work, so that it would be obvious that what is a generalized pipeline of that particular category it's like a kind of a general way to approach that particular method based on the category it resides in. So if you want to go into the details, please take a machine learning course, and following are some platforms which offer nice course in terms of machine learning. Fast.ai is, as I call it, a bottom-up approach where you start learning with a practical approach, while Coursera and deeplearning.ai are top-down approaches where you start from theoretical aspects and eventually go towards some of the practical aspects. So why we use machine learning? We use them to make predictions on data. That's obvious. That's why it's like a kind of making an autonomous decision process making system, and arguably it has been the greatest export from computing to other scientific fields, because it can be used to a variety of fields such as finance, or such as quantum physics, and there are many other applications which actually use this, such as linguistics. So natural language processing is one of a kind of advance to the field of natural language processing. It's like a kind of a merger of linguistics and computer science. And similarly, there are other applications like medical image processing. So basically, machine learning has proven to be effective if it is integrated with the underlying principles on the underlying technologies of that particular field. So if we consider the medical image processing, if we consult with the doctors and prepare a gold image or gold standard data set which has the annotations and the labels, then it can be used for performing an autonomous decision making process. So this is a kind of an integration of human experts and the machine learning, what you say is paradigm, to make an autonomous decision process. So statisticians might disagree with computer scientists on the true origins. Of course, sometimes machine learning is also considered to be a glorified statistics, or sometimes it is considered to be applied statistics, sometimes it is considered to be something else. So basically, the origins of machine learning is not exactly from the statistics itself, but most of the statisticians believe that it's a kind of an extension to statistics, but that's not true if you see it from the perspective of a computer scientist. Now we will focus mostly on the machine learning in the context of computer vision. So we'll not go into the details of natural language processing thing. We'll not go into the details of like sensor data analytics or financial data analysis. So we'll not go into the details of those particular things, because those are related to the modality of text or the modality of speech or something like that. So we will not cover those aspects in our class. We will stick to the applications which are closely related to computer vision, and some of them are face recognition, object classification, and scene segmentation. So some of the examples of face recognition can be found here. So if you want to perform this kind of face recognition, you can go to my GitHub page, that is github.com/Sandar-Ali, and you will find a pre-trained model which can be used for face detection. It uses SSDNet, so it is kind of a fast and can be applied to both images and the videos. So some of the examples with the same pre-trained model are shown here. And then there is object classification, and object classification can be extended to object detection as well, and some of the applications for object detection can be found here. So this implementation uses RetinaNet for detecting objects, of course detecting and recognizing objects at the same time. So these are some of the other examples for object detection. and then there is scene segmentation. In image segmentation, at the end of the lecture I already told you about semantic segmentation. So basically semantic segmentation is a kind of supervised learning which actually segment the image with respect to their labels, and it can be performed for scene segmentation, it can be performed for object segmentation, and vice versa. So basically this is one of the examples of semantic segmentation, and if you could extend it to objects, then you can have this kind of result. And this is of course my re-engineered results for these kind of images, and this is another example. This is one more example to this, and this is also another example for semantic segmentation. Now basically if you could ask me that what is the main modality or what is the main characteristic because of which ML is so popular, it is the data itself, and it needs a lot of data to perform a good recognition or to perform a good detection. So as Peter Norvig suggested, the unreasonable effectiveness, it's like it is proposed in its paper, The Unreasonable Effectiveness of Data, which was published in IEEE Intelligent Systems in 2009. He stated that invariably simple models and a lot of data trump more elaborate models based on less data. So it's like if you have a model based on less data and if you have a model based on a larger volume of data as compared to the previous one, then most probably the model which will be trained on a larger data will generalize better. Why I say generalize? Because many times you can achieve a good training accuracy, but maybe you cannot achieve a good testing accuracy with that. So by generalizing, I mean that it can generalize better if you have a large amount of data rather than if you have a small amount of data. It may achieve good training accuracy, but it might fail when testing it on a new sample which has not been seen before by the training model or by the computer or by the system. So one of the data set which is comprised of a lot of data is ImageNet, and it has a kind of a 1000 classes. 1000 classes, I mean it has images for 1000 object categories, and it is comprised of 1.2 million images approximately, out of which 100,000 images are dedicated for the test set. And most of the times the networks or the machine learning algorithms which are trained on ImageNet are evaluated through top 5 error, like top 5 predictions of that particular object. And this is the details. The more details for the ImageNet can be found in the paper ImageNet Large Scale Visual Recognition Challenge, which you can find on arXiv very easily. And this is the example of top 5 predictions for a particular object. So you can see that for this you can predict leopard or jaguar, cheetah, snow leopard, Egyptian cat, and if you want to consider the top one, then consider it like you can just extract the category which has the higher probability or the highest probability. But in this case, if you will see that this particular pink or a kind of a mixture of red and pink actually represents the actual label. So here it actually classifies correctly. In the top one case, this one also classifies it correctly with top one label. This also classifies it correctly, similar to this. But in this case you will see that the actual label is this, but the highest probability is convertible. So you can see that why we take the top 5 stuff, like top 5 labels. And similarly for the mushrooms, this is the actual label, but the highest probability is for agaric. And then there is no actual label here, and there is no actual label here. So you can see that there are some misclassifications as well. Now in as previously I suggested that from 2002 or 2004 we were mainly focusing on the handcrafted features such as histogram of oriented gradients or scale invariant feature transform, local binary patterns and so forth. But with the advent of deep learning architectures, we have achieved a kind of a better accuracy with respect to the traditional computer vision algorithms. Like if you can see here, in 2012 we achieved the same accuracy which have been achieved, which is kind of a best for traditional CV. We achieved it with deep learning at the start of that particular era, and in 2015 with Google Microsoft, they actually proposed GoogleNet. We beat the best human score in the ImageNet challenge, and you can see that we have achieved almost 100% accuracy on ImageNet. But there are some other pre-trained networks which perform better than GoogleNet, such as ResNet 150, DenseNet 201, and there is DarkNet, and there are Inception ResNet V2, Inception V4, Inception V3. So there are many variants to the GoogleNet which was proposed in 2015, and still there have been a lot of research conducted to improve those results and to improve a kind of the performance of deep learning architectures while reducing the amount of data which it uses to train the network. Now the machine learning problems are actually represented in this particular table. So the left side denotes or represents the data modality, like if the data is discrete or if the data is continuous. By discrete I mean discrete labels. So if your data has discrete labels, like let's say your data have objects, so the objects are kind of discrete, they are not continuous. So object recognition can be considered as a discrete problem, or like dividing the data into different clusters, different finite clusters, so it could be a kind of a discrete problem. But if you consider a kind of a regression problem like predicting house prices or financial time series data, so mostly they are considered as a regression problem rather than the classification problem, and the data modality is mostly represented as continuous data, not discrete data. And similar for the unsupervised learning, the continuous data, the combination of unsupervised learning with the continuous data can be referred to as dimensionality reduction, which we will going to be discuss not in detail but in an abstract manner. Now these are some of the methods which are related to dimensionality reduction, which is PCA, ICA, LLE and ISOMAP. PCA refers to principal component analysis, whereas ICA refers to independent component analysis, LLE is an acronym for locally linear embedding, and ISOMAP is an acronym for isometric feature mapping. So principal component analysis, what it does is it creates a basis where the x's represent the dimensions of variance from high to low, and it finds correlations in data dimension, that how the data is correlated with respect to the other dimension which you are trying to visualize here. So it produces best possible lower dimensional representation based on those linear projections. And what it does is it subtracts the mean of data, computes eigen decomposition, and then eigenvectors can be represented as direction of variance and eigenvalues can be represented as magnitude of variance. So let's see an example of this. Let's take an example. Let us draw an arbitrary black line through the set of points and draw perpendicular lines to this newly constructed black line from all of the points. The point where these red lines touch the black line is called the projection of that point on the line. So this projection is the new property or characteristic which the PCA will construct. This projection will be a linear combination of the original variables x and y and will be of the form ax plus by. Now how do we find such a black line? where these projections have the maximum spread or variance, and which also allows us to reconstruct our original points from the projections easily. That is the main question which lies, which is the underlying principle of the PCA itself. So let's look at the makeshift animation here for a while. As the black line rotates, the spread of the projections also change on the black line. If you observe closely, the maximum spread or variation of the red dots occur when the black line is roughly at 2 o'clock. The red lines perpendicular to the black line depict the distance of the projection point from the blue point, which is also the error in reconstruction of the original point from the projection. Stare at the animation for a few minutes and you will notice that the sum of the distances of the projection also occurs when the black line is at 2 o'clock. This sum of distances is also the total reconstruction error. PCA finds this black line and the projections for which the variance of the projections is maximum and the reconstruction error is minimum. So it's like killing two birds with one stone. So that is the underlying principle of the PCA. So in this representation you can see that we have the first principal component in the form of major axis and the second principal component in the form of minor axis. Basically you can get more information from this link here which I have mentioned, so you can go through this link and you can get more information. And similarly, if you want to get more information on the intuitive explanation of PCA, I would recommend a link which has been embedded here, which is quora.com. What is an intuitive explanation for PCA? So you can go through this link and I think you will have more information on the principal component analysis itself. Let me see if I have okay, so it's not here. So just go through the link and go through this link and you will be able to find a good example with intuitions regarding the principal component analysis. Now, one of the applications of principal component analysis was the face recognition using eigenfaces. This is actually the ATT face database, which was formerly known as ORL database, which has 10 pictures of 40 subjects each. And this face database can be found at the link here. Let me show you. So this is an example of face classification as well. I think this code is written for MATLAB, so you can go through this code and you can see that how you can actually perform face recognition. Okay, so this is one of the examples and one of the applications of principal component analysis. Now this in eigenfaces, what we do is we construct the mean face, we extract the mean face, and then we compare it with the other faces on the basis of variance, which is eigenvectors, and we classify whether it's the same face we are looking for or not. So this actually is proposed. This was proposed in a paper in face recognition using eigenfaces, which was published in 1991. The CVPR conference, which is one of the flagship conferences in the field of computer vision. Of course, there is one of the implementations by this guy, the Kosher L WordPress.com. So if you can see, if you can go through this link, you will find a detailed explanation that how you can use this eigenfaces for multiple applications like face detection, and then you apply the principal component analysis, and then you can actually perform the gender prediction as well by using support vector machines, which is a supervised learning. We will see it in the later videos for this week. And this is a kind of a demonstration, so you can also use this link to find out more about how we can apply PCA in certain type of applications. Now let me stop here, and then in the next part of this video we will focus on the clustering aspect. and we'll see that how we can solve this clustering aspect using unsupervised learning with discrete data. Currently we were discussing about the unsupervised learning aspects using continuous data. So let's see an example of clustering in the next set of videos for this week. Thank you.